let's start the lecture of having said this. This would be the last lecture in this module, and we are talking about dynamic matrix control. So, finite step response and state space model. And again, we have done this multiple times. So, I will quickly just recap. And this is the multi-step prediction. So, not much difference between the multi-step prediction for dynamic matrix control or MPC. Okay. You basically what we have done, state space MPC, what we have done is we have replaced this y with this x. What is y tilde? Y tilde is nothing but information that is carried forward for prediction of future, which is essentially the definition of state. Okay. This m over here, we said this was an upward shift operator. Okay. And briefly in one of the lectures, I also said what would be a matrix representation of that upward shift operator as well. It is 0 I 0 0 0 0 0 I 0 0 0 blah 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 until the pth row, right. So, that would be an equivalent if we want to look at as a state space equivalent. Okay. Likewise, there is a way that you will be able to get your capital M over here. Okay. Now, state space MPC comes in two different forms. One is the formulation that I have written over here, which is a U based formulation, or to have a commonality with what we have done in the industrial MPC, we could have also the rate formulation. Okay, and I will talk about the rate based formulation. Okay. So, the rate based formulation is nothing but you have the delta u instead of u. Okay. And we can, and both of those are equivalent but different forms. They have certain properties which are different from each other, but yeah. Now, if multi-step prediction you want to also include the effect of disturbances, okay, and same thing will get included there as well. I will just put E hat k. Okay. This is something that we will talk about in module 9 of this course. Okay. This would be something that the MPC toolbox will handle for you. Okay. How does it handle and what we need to do in order to ensure a bias free tracking? We will talk about that in module number 9. Okay. The idea is the same, is if we do not have the EK over here, then there will be a difference in the model prediction and the actual planned behavior. We are just moving the model prediction up or down to match the planned behavior. That is what we are doing in the step response matrix case. We actually use something called an observer and predictions based on the observer in order to do this correction in state space matrix. Okay. Now, why are those two things a little bit different? They are a little bit different just because of the structure of your state. In case of a step response matrix, the state is nothing but predictions of future output. So, all you need to do is move all the future outputs by certain amount. But let us think about a reactor. Your states might be concentration of A, concentration of B, temperature of the jacket, but your control variable might just be concentration of A and nothing else, right. So, based on concentration of A, you can't just arbitrarily move everything by the same amount. If the error in concentration of A is 0.1, does not mean that the error in temperature would be 0.1 also, right. So, it is not immediately known how you are going to move those values. So, how to do that? To get some kind of a theoretical idea, we are going to spend the next 3 weeks talking about the classical linear control theory, which is we are going to talk about stability, controllability and reachability properties in the next module. In the module after that, we are going to talk about estimator, and the module after that, we are going to talk about linear quadratic controller. These 3 concepts or rather the latter 2 concepts in the next 3 modules, we are going to then use in module number 9 to link it all together, and that is the idea. So, between now and quiz 2, we are going to do this, talk about linear classical control theory, and then bring the concepts of industrial MPC, the DMC implementation, and the classical linear control in order to talk about state space MPC. Okay. Having said that, not having the knowledge of linear classical control will not be a deterrent for you to solve your project 1. Okay. So, the idea of project 1 is get a feel for how MPC works, see for yourself how MPC works, and then learn the theory behind it. Okay. So, part 1 and part 2 of this course, learn the theory and then implement. Part 3 of the course, implement and then learn the theory. So, I am kind of trying to use 2 different approaches in different parts, so that we can kind of get a better learning in this course. Okay. So, that is the idea behind this. Okay. So, now when we talk about multi-step prediction, what do we have? We have SU, we have discussed, why am I saying discussed previously? Let me just write SU, no. Okay. Okay. When we are talking about your problem 1 of your assignment, okay, we are going to require for problem 1 this, this and this. Sorry, problem 1 is this, this and this. That is what we will require for problem 1. And for problem 2, we are going to require this, this and this. Okay. For any realistic situation, you will require both of them. Yeah. The other thing is, when you are coding, you have the freedom of coding all of it. Okay, you do not have to ignore EK. What is going to happen in problem 2? There is no plant model mismatch, therefore your Y plant is going to be equal to your Y model, your E is going to be equal to 0, it will just be ignored. Okay. So, it is not like you are doing one thing for one case, another thing for another case. There is no measured disturbance, delta D is 0. There is no plant model mismatch, E is 0. So, that particular part is just going to drop out. Okay. So, if you write one set of code for a more general case, okay, you can use it for all the 3 questions that have been asked, problem 1, problem 2a and 2b. Yeah, right. Got the question? The question was, for example, in the problem statement, we had steps at 0, 12 and 20, right. So, delta D 0 will be 0.5, delta D 1, 2, 3, 4, 5, 6 up to 9 will be 0, right, at 10 and 11 will all be 0, at 12 there is one more delta D coming in. Okay. Very important to remember that when we talk about step response MPCs, inputs as well as measured disturbances, we are talking about deltas only. Okay. So, yeah, use delta U, okay, delta D, yes, yes, your model is based on delta U and delta D. Okay. So, if you look at my code that I have uploaded, right, the UK equal to UK minus 1 plus delta U is used only for two reasons. One is finally we want to plot what U looks like, okay, and delta U may not make sense to anyone except really experts who have done the coding and who have worked with that system. Otherwise, delta U does not make sense for anyone. So, that is why we need to extract that U. Okay. So, if you do not have constraints, the only reason for calculating U was to plot. It is not really used in industrial MPC. The only other place where it is used is because you have input constraints. That is the only other place it is used. So, you need UK minus 1 in order to get that input constraint. Otherwise, you do not even need to worry about U. Okay. So, yeah, good question. No, I did not say delta D as constant. I said that, okay, 2 different things I have said, and I do not remember whether the latter thing I have said or not. D is constant, okay, which basically means at the first instant, at the kth instant, delta D is that value, after that it is 0. In response to a question after the class, and in case you have overheard it, in response to a question after the class, I said that there are certain instances where you know that the disturbance is of a ramp type nature, in which case the disturbance is not like this, the disturbance is this. So, therefore, you use delta k plus 1 k plus 2 equal to this. For our course and for most chemical engineering problems, not relevant at all. Problems like an integrating type of a problem, this is relevant. It is also not relevant for a problem like inverted pendulum, because you do not use step response MPC for control of unstable systems. Step response is only for control of stable systems or nominally stable or integrating systems. Okay. The MPC for integrating systems we have not covered in this course, the step response MPC for integrating systems. The state space MPC is an all weather friend. You can use it for unstable, stable, marginally stable, all type of systems. Okay. Again, last 2 minutes was a segue in response to that question. Just keep that in mind. Okay. So, let us now talk about if we have a state space model. So, if we have a state space model, you have x k plus 1 equal to a x k plus b u k, right. So, you can write right, and you can go on. Okay. You see 2 plus 0 equal to 2, 1 plus 0 equal to 1, 0 plus 1 equal to 1, okay, that is how it is going to be. So, you are going to have a to the power p x k at k plus a to the power p minus 1 b u k plus a to the power p minus 2 b u k plus 1 right. Actually, it will be p minus m, k plus p minus 2 k plus p, k, yeah, okay. Each of these we can multiply this with c. What will be the left hand side be? It will be y k plus I at k, right. So, you are going to get right. So, you can write y second step is y of k plus yp of k is yk plus 1, yk plus 2 up to yk plus p. What is yk plus 1? It is Ca multiplied by x plus Cb multiplied by uk plus 0 multiplied by uk plus 1 plus 0 multiplied by uk plus 2 plus 0 multiplied by uk plus p minus m. Okay. So, that is why the first row is Cb 0 0 0. Yk plus p, okay. So, x, this you got this particular thing, okay. So, I just multiplied by c, left hand side is c multiplied by x k plus p at k, which is y k plus p at k, okay. The first term is c a to the power p multiplied by x k or x k given k, but yeah, why be lazy. Okay. The next term is going to be c multiplied by a to the power p minus 1 multiplied by b. The one after that is that multiplied by uk will be there, right. The one after that is c multiplied by a to the power p minus 2 multiplied by b, so on and so forth. Okay, let me write this in a better way. Same thing, okay, without the delta. Maybe I will erase this delta over here, that should become clear. Okay, let me write this in a better manner. Okay, fair enough. Okay. Now, just one thing, I am showing the state space MPC part over here for two reasons. One, for sake of completeness, because we are talking about MPC right now. You know, I just wanted to show you that there is exact parallel between state space MPC and step response MPC. Okay. This we will redo this in all details again in module 9. Okay.